I've just handed out the curve that is going to help you with your demand estimation. Remember that you have to do peaking factors, and you can know your peaking factors with this curve that I've handed out. And we went over that last time in class. I show you in the notes that I've posted on MU Online how to do some peaking. You may end up using different peaking factors than me. I think I used 3.25 for the maximum hour and 1.8 for the maximum day. That's based on some other information from a different book, but here it would say that the peak hour is maybe 2.7, and you'll have to do the average to find the max day. I'm not going to eyeball it, but any questions that you want to ask about the project before we get into talking about channel flow today?
On the spreadsheet, what's the compound? It says COM.
Commercial, and so if an area has both residential and commercial, then that's talking about the population density, like in terms of commercial users. And so I think loop 1 has both residential people living there and then also people who are there for commercial reasons, you know, like businesses or industrial stuff. Okay, so 48 hours from now, you'll be turning in your draft guess of the water demand in that network. Our next assignment, homework 7, is going to be due on the 4th of March, and you can get started on those problems if you like, and I'll give you the handout in class on Wednesday. But I think you probably have your hands full with the demand estimation until then. Here's just a couple of other points that at some point in the project, you're probably going to want to submit PDF files of, for example, printouts of your map. And there's a free PDF creator available online. If you don't already have the full version of Adobe Acrobat, this program will allow you to print a PDF, create a PDF almost as though it's just an ordinary printer. And so that if you're uploading files onto MU Online, that they can actually be viewed. You know, if I want to get a map from you, you can make a PDF of it. Remember that for the fire flow, it's not the entire block that's on fire, it's just a single structure, and peak flow, fire flows don't need to be peaked in the same way that your ordinary residential demands do. And so you'll be peaking the residential demands, but then adding the fire flow on top of the average daily, not on top of the hourly flow.
The table is basis fire flow on square footage of buildings and like building confirmation. Would it be okay to use those values for there?
Well, no, unless that table takes into account the material, like what it's made out of, and the spacing to other buildings. Because the NFF method that I've provided you the reference for does take those things into account. The square footage is one of the variables, the material, you know, whether it's wood or concrete or whatever, and then also adjacency to other structures. Yeah. All right. Remember from fluid mechanics that there are two types of flow when we talk about change with respect to position. There's uniform flow, where velocity doesn't change with respect to position. And uniform flow is characteristic of streamlines that are straight and parallel. So on the right, image B is water flowing through a pipe, and the streamlines are parallel. On the left, we have an inclined cross-section of a channel. It's open to the surface. You can tell that it's open because of the tiny little triangle there. Oh wait, maybe that's a streamline triangle. These cross-hatched black lines mean it's meant to represent the waves of water. So that's how you can tell that it's open to the atmosphere. Non-uniform flow is where the velocity is changing with respect to position, and so that the streamlines are curved, aren't parallel, and so the velocity is not constant with respect to position. One element of the velocity, either the magnitude of the velocity, in this case, it's getting faster, speeding up. In this case, even though the magnitude of the velocity, the speed may be the same during the rotational flow, the fact that the direction is changing means that 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 factor, the vector of velocity is changing because the direction of the speed is changing over time. Steady flow is where conditions are either changing or not changing with respect to time. In the case of steady, they're not changing. Over time, velocity is constant. Unsteady means that just over time, either the magnitude or the direction of flow is changing. And here's a series of photos that represents unsteady flow. This is a culvert as it begins to collapse underneath a roadway. And so before and after. And that culvert failure caused soil around the edge of the culvert that it was buried in to be swept downstream, and ultimately the entire roadway collapsed and was washed downstream. So now it's just a big flooded river where it used to be a solid road. Different types of channels are classified by their geometry, and a prismatic channel is something that usually is man-made because it has a constant cross-sectional shape in the direction of flow, so that if you take a cross-section here and some distance from here, the cross-section hasn't varied, or that it's varying in a constant way. The slope is constant, the alignment is straight, and so here's a trapezoidal cross-section that shows the water here, and you can see that both sides of the channel have the same side slope. The side view has a constant channel slope, and in the top view it's a straight uniform channel that wouldn't occur in nature. We can tell that it's made by humans, whereas a non-prismatic channel has variations in one or more of those attributes. It can have an irregular cross-section where there may be certain elements of the channel that are deeper than others. There could be a ledge that's corresponding to a floodplain of different return period storms. It may be that ordinarily the water is within this channel and then it floods occasionally, and you can see that there might be a wider channel associated with the sediment transport that occurs during a really big event storm. This is the slope of the channel, and so you can see that there may be sections with a very steep slope, others that are relatively mild, and then from a top view, it's a meandering stream. So which of these two do you think is easier to solve problems on? Prismatic, absolutely. And so we're going to spend probably the first 2/3 of this module of the course talking about prismatic channels, because the calculations used to find the depth of flow or the flow rate that can be conveyed by a certain geometry, those calculations are a lot simpler for a prismatic channel where the flow is steady and uniform. But we do have the tools that we can calculate the flow of a non-prismatic channel, but to find out the depth, especially when you have an irregularly sloped channel bottom, is very intensive. You have to go in segments. You have to say, well, I'll look at the problem from here to here, and then from there to there, from here to here. You have to do it in little steps, and you can either make assumptions that within that step it's prismatic, or there are iterative methods that you can use to find where water depth actually is, and breaking the channel up into lots of little pieces and solving it lots of times over and over and over, finally find where the water level is. And we will get into that in the latter third of this module. In your text is a table that shows channel geometry for a variety of different prismatic shapes. And of these, the most challenging to deal with, believe it or not, is the circle. It's very difficult to find out what the cross-sectional area, wetted perimeter, and so forth is for a circular channel that's only partially full. If it's half full, that's easy. But if it's not half full, we have some pretty complicated formulas for finding the area, wetted perimeter, and so forth. And we actually have to measure the angle that the surface makes with the center of the pipe, and that angle is expressed in terms of radians. And we will eventually get to pipes that are flowing partially full when we talk about flow through sewer, because most sewer networks are circular pipes, ordinarily concrete pipes, and most of the time they aren't full. And so the partially full pipe problem is very significant when it comes to drainage of storm drains and sanitary sewage. But to start off, most of what we'll do will either be rectangular channels or trapezoidal. So you may want to put a little tag or highlight table 10.1 because you'll be coming back to it periodically through the semester. Turbulent flow determined what in pipes? When we had a pipe and it had some roughness elements, why were we interested in knowing if the flow was turbulent versus laminar versus turbulent, or if it was all the way into the fully turbulent range? When did it matter? Okay, when you're calculating the losses, right. It mattered because resistance changes based on the degree of turbulence. And I've sort of exaggerated the roughness elements of the pipe. And remember that we were talking about there being some imaginary boundary. And does anyone remember what this boundary is describing? That's right. There's a region, even if you have turbulent in most of the pipe, there's a region very close to the pipe where it's the laminar sublayer. And that same phenomenon will exist in open channel flow as well, where close to the boundary of a solid conduit that water is flowing through and the fluid itself, very close to that boundary, there's going to be a laminar sublayer where the velocity of the fluid is very low. And so we'll be interested in whether or not the roughness elements protrude out of that laminar sublayer. So the three types of turbulent flow, we've got a velocity profile, and that's different from the velocity profile that I often draw when we've got a pipe. This being a pipe, my velocity profile, if it's a laminar flow, is like that. It's parabolic. So why do you think that in this case, for open channel flow, it doesn't have that same parabolic shape? Nothing on the top. There's no resistance. There's air on the top, and the air provides a little bit of resistance depending on the velocity. Sometimes you'll see a velocity profile represented for an open channel, and rather than what I've shown, sometimes what they'll actually show for the velocity profile is more like that. So that there'd be a little bit of a velocity decrease as you get close to the surface. Sometimes they'll say that it's actually 0.9 times of the way. If you go 10% into the depth, that's where you get the maximum velocity for a river. But at the surface, it's not the maximum velocity because it's in contact with the air, and the air is slowing it down just ever so slightly. So in this case, there's going to be a turbulent zone and a laminar zone. Here again, I've exaggerated the thickness of the laminar zone. The laminar zone, really, if you think about the really slow velocities that have to exist for laminar behavior, it's going to be just a couple of millimeters in thickness is all. And we've got some roughness elements. Boy, if you knew how long it took me to put this animation together, you'd either be impressed or disgusted. So let's go through that again so far. Okay, we've got a channel with water, and then we've got a velocity profile, and because of differing velocities at different depths, there's a section of the flow that's turbulent and a section that's laminar. And in this case, you can see that the roughness elements are fully submerged in that laminar zone. So that laminar zone is sort of like a cushion of water that it doesn't have a lot of random turbulence in it. Remember that when we visualized laminar versus turbulent flow in the lab with that long, thin tube where the dye was being injected, that when conditions were laminar, the dye was in a straight line. But when conditions were turbulent, it was like a squiggly line. There was a lot of random variation in velocity throughout the tube, so that in a case like this where the roughness elements are fully submerged by the laminar layer, it's not like there's a lot of ricochet, velocity, some random velocity ricochet and causing even more turbulence. So smooth flow is when those roughness elements are submerged in a laminar sublayer. The next kind of turbulent flow is when it's transition. And it's funny to think, if I just go back here, smooth turbulent flow. Doesn't that almost sound like an oxymoron, a contradiction in terms? Smooth but turbulent. Okay, the reason why it's smooth but turbulent is that most of the flow is turbulent. The majority of this depth is going to be turbulent, but it's smooth where it counts. And where it counts is at the boundary. Transition, turbulent. The majority of the flow is turbulent, but the thickness of the laminar layer is equal to the height of those roughness elements. And then rough turbulent flow is when the roughness projections are outside of the cushioning laminar sublayer. And so these little mountaintops of roughness are projecting into the zone where there's lots of turbulence and random behavior, so that a particle may hit that roughness element and then be projected backwards, and there's going to be even more losses in the rough turbulent flow than there would in the smooth turbulent flow. And which range we're in some way determines the methods we use for estimating energy losses. And it's certainly going to have an effect on how much energy is lost. Remember that the big equations that we used in pipe flow was probably the energy equation and continuity. Those were the main two. And then within the energy equation, of course, there's different ways to calculate head loss. There's another equation that we're going to be using a lot in open channel flow, and it's the momentum equation. And the momentum equation is what we'll use to account for the fact that energy isn't always conserved in open channel phenomenon, but sometimes we can solve problems by looking at conservation of momentum. Now let's just walk our way through this figure here and take a look at between point 1 and point 2 what's changing. And at location 1, this is open to the air, so the triangle and the little horizontal black lines indicate like atmospheric air above the water surface. The triangle here is a pressure distribution. So the deeper you get into the water, the pressure is increasing. And at 2, there's less pressure because the depth isn't as deep. Since we've got a changing water depth, since Y1 is deeper than Y2, that tells us we don't have uniform flow. So this is non-uniform. And we have to ask ourselves, why is it non-uniform? What is it about this that could be drawing down the depth? Any thoughts on what could cause non-uniform flow like this?
Just the very end of the flow, like flow is just filling up the channel. Maybe it look like that.
Okay, so you're saying that like if the flow rate was increasing, like if it was deeper on the left because this is like a wave that's traveling downstream. Okay, that is a possibility, absolutely. So it could be that not only is it non-uniform, which is what we can see from the picture, but maybe it's also unsteady. In the case that he describes, unsteady flow would be somebody's opening up the gate of a dam or something, and so there's this big surge of water coming downstream. That could be it. But it could be that it's steady conditions, that it's going to look like this in an hour, the same as it looks like it now. It could be that maybe it's approaching a drop-off. And think about waterfalls, for example. If the part that we are looking at doesn't show the waterfalls, but it could be that the water is drawing down because it's accelerating before it falls over the edge of a cliff.
What if the channel was getting wider?
That's another thing that can cause non-uniform flow. And the interesting thing is that making a channel wider, you'd think, oh, absolutely, it's going to make it shallower. Sometimes making the channel wider actually makes the flow deeper. And that's one of the interesting things that we're going to do this semester, is try and figure out how the water reacts to making the channel wider? Or what if we put a step in the channel? You'd naturally think, well, if you put a step in the channel, it's going to get deeper. And sometimes it gets shallower, actually, after it flows over an obstruction. And so it behaves in unexpected ways, and you really have to do the calculations to be able to predict whether it's going to get deeper or whether it's going to get shallower in any of those cases. There's 3 different lines that we have to be aware of, 3 different slopes. There's the slope of the energy grade line, S sub F, and that's not pictured here. The slope of the energy grade line is above the water surface. It's that imaginary line that is the water surface plus the velocity head above it. So the slope of the energy grade line, then there's the slope of the water surface, and then there's the slope of the channel. So 3 slopes that we have to be aware of. In uniform flow and uniform steady flow, all 3 of those slopes will be equal to each other. The slope of the water surface and the slope of the channel and the slope of the energy grade line. Okay, so if we do a force balance and consider what are the forces in the direction of flow, in the x direction, we have to consider the fact that there is some velocity at 1 compared to a velocity at 2 is going to be different, because if, assuming the channel width is constant, if it's getting shallower, then the velocity at 2 has to be faster. And so because there is a change in velocity, but yet the flow rate is the same, the mass flow rate is constant, but the velocity is changing, there's going to be a difference in forces. And we can relate that difference in forces and the resistance on the bottom of the channel, the resistance to flow, and from that find a relationship between the velocity and the slope of the energy grade line. And this formula, the F that's shown here, is the same Darcy-Weisbach friction factor that we've been using for pipe flow up till now. But we don't ordinarily use the Darcy-Weisbach friction factor in open channel flow. Shear stress isn't something that we can really measure, and so measure directly. And so what we have to do instead is find ways to estimate the roughness of a surface, and that's where the Manning's equation comes in. We'll be using the Manning's equation almost exclusively for open channel flow, whereas in pipe flow we use Darcy-Weisbach or the Hazen-Williams equation. We'll leave them in pipe flow and now use Manning's equation almost exclusively in open channel flow. And remember that the difference between the energy grade line and the hydraulic grade line, in open channel flow, the hydraulic grade line is the water surface itself, whereas the energy grade line is above the water surface by a distance of v squared divided by 2g. So EGL is velocity head plus depth plus elevation above a datum. HGL is just the depth plus elevation above the datum. So compared to the pipe flow, this is open channel. Pipe flow, the EGL was velocity head, pressure head, and elevation. Instead of being pressurized, since open channel flow is open to the atmosphere, its depth takes the place of the pressure head. The slope of the energy grade line is looking at, in the direction of flow, in the x direction of flow, how the sum of those things is changing. Okay, so here's the energy grade line. The slope of energy grade line S sub F. Okay, so it's the slope of the energy grade line. You just look at where is all of the energy. The energy is either in the depth, the elevation above the datum Z, or the velocity head. And so the slope of the energy grade line just looks at, in the x direction, in the direction of flow, this is the x direction. You can see the little x here. So that's saying, not in the horizontal plane, but in the direction of flow along the inclined path, which essentially our slopes are going to be so mild that just like it was in pipe flow, we're not going to worry too much about whether it's the horizontal length or the inclined length. Those two are going to be numerically equivalent. But the slope of the energy grade line is just looking at how does the sum of the elevation head, the depth, and the velocity head change in the direction of flow. The problem is that this curve illustrates the problem perfectly. The slope here, there's some slope, but the slope here is different. This is a curve that's changing. And so between 2 points, there's not one single slope that you can say, well, I can go from 1 to 2 by just using that single slope. There's going to be a variable slope between them. And so finding the new depth isn't as easy as saying, well, I know the depth here, and there's some one slope between them. It's going to be us breaking it up into little pieces and treating a curve like a series of straight lines in order to find the new depth. That's to give you a glimpse or a preview of some of the numerical methods we're going to have to utilize to find the slope of the energy grade line's effect on depth. If we do use the Darcy-Weisbach equation to find head losses, here's how we can implement the Colbert equation to find F. So the Colbert equation, like it was in pipe flow, is always valid. We don't have to worry about just a range of conditions where it will give us an accurate F value. And so you can find the flow rate using the Darcy-Weisbach equation, building in the expression for F. That doesn't look very fun to use.
Is that R hydraulic rate?
Yes.
Dr. Wade?
Yeah.
That logarithm just assumed to be base 10?
Base 10.
Okay.
Yeah. I don't think we'll use this at all, but there it is. The energy equation in pipes, remember, is pressure head, velocity head, and elevation above the datum at 1 versus 2. The pump is over on the left-hand side, and the head loss is on the right-hand side. We've subtracted the pump from the left. I'm sorry, from the right. In open channels, the energy equation substitutes depth for the pressure, and there's no pump. There could be a screw pump. Remember that when we were talking about pumps, there could be something that's lifting the water from point to point. But we're not going to consider pumps in the same way that we did in pipes. In open channel flow, we'll just be looking at the natural variation of a water surface between 2 points. But there are head losses, H sub F. There are head losses. And between these 2 points, between 1 and 2, if it's a uniform steady flow, the head loss is equal to the elevation loss between 1 and 2. So delta Z, the elevation of the channel bed above the horizontal datum, is going to be equal to how much energy is lost between 1 and 2. In this case, the slope of the energy grade line is equal to the channel slope.
Is alpha considered to be negligible again?
Yes, yeah. Especially true in open channel flow because in open channel flow, the velocities are much lower than they generally would be in pipe flow. And there are exceptions to that. Flow over the top of a dam spillway does get moving pretty fast. But most of the time, especially in natural channels, the slope would be maybe at most 2%, 3% slope. And so the velocities will be pretty mild by comparison. Head is measured, and we talk of head in the same way that we did with pipe flow. It's the sum of all three terms. And when we were doing the problem, the three reservoir problem, for example, and we found the head at junction D, that was just by adding up all of the terms of the energy. In pipe flow, sometimes we neglect the velocity head, though. For example, when we did the three reservoir problem, we just used the pressure as an indication of what was the real source of the energy at a location. And there are times when we'll do the same thing in open channel flow as well, where the amount of energy that is existing as the velocity head is very, very small compared to the depth and the elevation above some datum. The energy grade line is just a plot of the total energy, the total head with respect to distance. These are the types of questions that we're going to be tackling for the rest of the semester. If we have a channel with a known geometry, it's a certain width, and it's made out of some sort of material like concrete, then we'll want to know what is the flow rate in the channel. If the depth of the water is a certain location, we know the slope. So corollaries to that may be how big would a channel need to be in order to convey a certain flow rate. And this year's senior design group, for example, there's different teams, and the hydrology and hydraulics group, half of their job is going to be sizing a channel and trying to figure out how big does it need to be for the flow rates we expect is going to be coming through this stream. Or if you have an existing channel, then you may want to know how deep will the water be for the given channel geometry, rather than if you actually have control over the geometry and you know that you only want it to be a certain depth. When it gets complicated is when we have an irregular channel geometry, like a non-prismatic channel, trying to find ways to calculate flow rate to accommodate irregular channel geometry, or if it's rectangular and then down the line transitions to trapezoidal, and then down the line the channel width changes again. That will be one of the complicating factors that we'll have to handle. Or if there are different roughnesses, if at one section of the stream it's a very smooth finished concrete, but then later on it may transition to a very rough, broken up concrete riprap. So these are just some of the questions that we're going to be taking a look at. And so the need to use Excel is going to be as great as it ever was. It saves us all kinds of problem and headaches when we have iterative problem solving, and we've got a lot of that through Open Channels. So just to give you a preview, remember, if we switch back to these announcements, that the big thing to be working on between now and Wednesday is the flow estimation for the project. And if you want to stop by before then, just to see if you're in the ballpark, I've got ballpark estimates. I'm not going to tell you what it is, obviously, but I can give you a thumbs up or a thumbs down. But the stakes aren't too high, because you're going to have time to correct any mistakes that you have in your work before the final project is submitted. So, all right, well, I'll see you on Wednesday, if not before.